Imagine for a moment, just for a second, you're standing right in the middle of a huge active construction site. If you close your eyes, you can almost feel it. It's a total sensory overload.
Oh, absolutely. The noise, the ground shaking.
Exactly. You've got that thud of pile drivers, shaking your bones. Cranes are swinging tons of steel way up over your head.
There's dust everywhere,
Yeah.
the smell of diesel. It's organized chaos.
It really is. But in all of that visible chaos, all that noise and machinery, there's this silent, invisible force running through the veins of the whole site.
An incredibly powerful one.
Incredibly, it's powering everything from the tower cranes to the lights, but unlike a falling brick, you just can't see it coming.
You're talking about electricity. And you're right, on a construction site, it's a completely different animal than what's sitting behind the wall in your house.
That is exactly what we're digging into today. We're doing a deep dive into a document that, honestly, most people never get to see.
Right, usually just lives in the safety office filing cabinet.
Yes. We've got our hands on this high-stakes training module. It was made for something called the ABM Project. And this isn't some, glossy Be Safe pamphlet.
No, this is a technical deep dive into construction site electrical safety and management systems.
And what was the first thing that jumped out at you? For me, it was how tough it is.
So the rigor. I mean, it's the absolute rigor of it. With most corporate training, let's be honest, you click through a few slides.
Answer the obvious question.
Yeah, don't touch the fire, and boom, you get your certificate.
Right, the check-the-box mentality. Don't stick a fork in the outlet. Congratulations.
This is the complete opposite. The assessment criteria here are, they're brutal. To pass this module for this project, you need an 80% minimum.
An 80%? I mean, think about that. In college, a 60 gets you a degree, right?
Yeah, 60 can make you an engineer in some places.
Yeah.
But here, a 75% is a flat-out fail. You are not getting on that site.
So why so high?
Well, it makes perfect sense when you think about the stakes. If you only know 75% of the safety rules for high-voltage systems, the missing 25%, that's where people get killed.
Mostly knowing how to ground a generator isn't good enough.
Not even close. You need near perfection because the environment is actively trying to work against you. It's wet, it's temporary, it's full of metal.
That really sets the stage. So, the mission for us today is to figure out the answer this training poses. How do you manage a high-power electrical grid in what is basically the Wild West?
Well, it starts with understanding it's not just a bunch of wires. It's a system, a hierarchy. The training calls it the electrical management system, or EMS.
Okay, the EMS. Let's break that down. I like to think of these things biologically. So if the whole site is the body, the EMS is kind of like the nervous system.
That's a great analogy, a really solid one. And if it's the nervous system, then right at the top you've got the brain.
The brain.
That's your main distribution board, the MDB. It's where the massive utility feed comes into the site. All the energy flows through there first.
So everything starts at the MDB.
Yep. And from there, power goes to smaller sub-distribution boards, the SDBs, which are placed all over the site. But here's the key part. The training really stresses this. It's not just about plugging things in.
Right.
It's about strict engineering. Two of the biggest principles are load calculation and segregation.
Load calculation? That sounds like something you'd do for concrete, not electricity.
You have to. You have to treat the electrical load like a physical weight on the system. In your house, if the lights flicker when the AC kicks on, it's just annoying.
Sure.
On a site, if a welding rig causes a voltage drop for the tower crane, that crane could literally drop what it's holding.
Wow. Okay, that's a terrifying thought. A power dip isn't just an inconvenience, it's a major safety failure.
It's a critical failure. So load calculation is knowing exactly what every single tool and machine is going to draw before you even plug it in. And then segregation is just the discipline of keeping those heavy loads away from the critical stuff.
So you don't run the big machinery on the same circuit as the lights.
Exactly.
Yeah.
Because if a saw jams and trips a breaker, the last thing you want is the entire stairwell plunging into total darkness.
That makes perfect sense. Panic in the dark is its own hazard.
It is. Now, the other big pillar here is earthing and grounding. We hear those terms all the time.
Right. Earthing, grounding. What's the core idea there?
It's simple physics, really. Electricity is lazy. It always wants to find the easiest path to the ground.
Okay.
The entire system is designed to make sure that path is a nice, safe copper wire and not, a person's body.
So if a wire comes loose and touches the metal case of a machine?
The current instantly rushes down that green earth wire into the ground and trips the breaker. Without that wire, the whole machine becomes live, and the next person to touch it becomes the path.
The source throws a lot of acronyms around here. RCCB and ELCB. I feel like I've seen those on my breaker box at home, but I have no idea what they do.
They do the same job, stop you from getting shocked, but in different ways. The ELCB is the older one, the earth leakage circuit breaker. It literally looks for voltage leaking onto the metal case of an appliance.
So if my washing machine casing gets hot, the ELCB trips?
Exactly. But the gold standard now, and what this training demands, is the RCCB, the residual current circuit breaker. It's much, much smarter.
How so?
It's like an accountant.
Yeah.
It measures the current going out on the live wire and the current coming back on the neutral wire.
It's balancing the books.
Perfectly put.
Mm.
What goes out must come back. If 10 amps go out, but only 9.9 amps return, that missing bit has to be going somewhere, maybe into a person.
And the RCCB sees that.
It sees that tiny difference, we're talking milliamps, and it cuts the power in milliseconds. It's unbelievably fast.
That's amazing. So we've got the brain, the EMS, but the training spends a huge amount of time on what I'd call the reflexes, relays. Why do relays get a whole chapter? They just sound like switches.
Because a switch is manual. A relay is automatic. It's the difference between you deciding to blink and your eye just blinking because a fly gets too close.
Ah, so it's a protective reflex.
Yes. And think about it this way. You've got a circuit with 10,000 volts. You do not want a person physically opening or closing that switch. It creates a massive arc flash. It's an explosion.
So how do you control it?
You use a relay. From a safe distance, you flip a tiny low-voltage switch, maybe just 24 volts. That little signal tells an electromagnet inside the big, dangerous unit to do the heavy lifting for you. It separates the human from the hazard.
But the training talks about them as more than just remote controls. It's about monitoring.
And that's the reflex part. These relays are constantly tasting the electricity. They're looking for abnormal conditions. If they sense an overcurrent, too much power.
They trip.
If they sense an earth fault, they trip. They don't wait for a human to notice a needle in the red.
The source lists a few specific types. Overcurrent, earth fault. I want to ask about thermal overload. Why is heat such a big deal?
Because heat is the silent killer of motors. Imagine a crane trying to lift something that's just a little too heavy. It won't stall right away.
It'll just try harder.
It'll try harder. And to do that, it pulls more current. That extra current generates heat. It might not blow a fuse right away, but over a few minutes, that motor will literally cook itself from the inside out.
Like a slow cooker.
It is. A thermal overload relay basically mimics that process. It feels the heat building up from the current, and it kills the power before the damage is permanent.
What about a time delay relay? That seems counterintuitive. Don't you want safety to be instant?
Not always. This is where it gets really clever. Think about starting a huge motor. For a split second, there's a massive surge of power, the inrush current.
Right.
If your protection was instant, it would trip every single time you try to turn the machine on. You'd never get anything done.
Okay, so the delay.
The time delay relay says, okay, I see a huge spike. I'm going to wait 2 seconds to see if it's just starting up. If the spike goes away, great. If it stays high, then it's a fault, and then it trips.
That's smart. It knows the difference between a startup and a problem.
Exactly. So we have the brain and the reflexes. But these sites are massive and confusing. You can't just look at a black cable and know where it goes. You need a map.
And in the electrical world, that map is the single line diagram, or SLD.
Yep.
The SLD.
I was curious about the name, single line. Don't these big cables have like 3 or 4 wires inside them?
They do. But if you tried to draw every single one of those wires for an entire site, the drawing would just be a mess of black lines, a bowl of spaghetti, unreadable.
I can picture that.
So an SLD simplifies it. It uses one single line to represent that whole bundle of wires, and then it uses standard symbols to show you the logic of the system.
So it's not a physical map. It's not telling you the cable is buried next to that big rock.
No, it's a logic map. It tells you this transformer feeds this panel, which feeds these 3 breakers. It's your #1 tool for troubleshooting.
The source says you use it for tracing fault locations. So walk me through that. The lights go out and say, Zone B, what do I do?
Okay. Without the SLD, you're just wandering around randomly opening boxes, which is slow and really dangerous.
Right.
With the SLD, you look at the diagram. You find Zone B. You trace the line backwards, upstream. You see it's fed by breaker 4 on panel A. So you go straight to panel A.
And if breaker 4 is tripped...
You know the problem is somewhere in Zone B. If breaker 4 is fine, you look further upstream on the diagram. It turns a wild goose chase into a systematic process. It's the difference between being lost in the woods and having GPS.
Okay, let's talk about the environment itself, the Wild West, as you called it. This whole system is temporary. The site is constantly changing. How do you even manage that?
That's the real challenge. And the training makes it clear. Temporary does not mean sloppy. In fact, the standards have to be even higher because the risk of physical damage is so much greater.
Physical damage from what?
Everything. Excavators driving over cables, cranes swinging into overhead lines. You can't just run an extension cord across the mud. You have to plan the routes. You have to do a site survey.
The document got really specific about underground cable laying procedures. It's not just digging a trench.
Not at all. You have to lay the cable in a bed of sand to protect it from sharp rocks. You put protective tiles over it.
Okay.
And this is critical. You have to bury warning tape about a foot above the cable itself.
Warning tape?
Yeah, bright yellow tape. So if another crew comes along next week with a backhoe, they hit the tape first. It's a last chance to stop them before they dig into a 10,000-volt line.
And then there's the biggest enemy on any construction site, water.
Water and electricity. A terrible mix. This is a huge focus. They talk about IP ratings, ingress protection.
I see that on my phone now, IP68 or something.
Right. It's two numbers. The first is for solids, like dust. The second is for liquids. On a site, you need equipment that can handle being blasted with rain. You can't use regular household plugs. The source explicitly bans them.
So what do you use?
Big industrial plugs, those round blue or red ones that lock together. They're designed to be watertight.
Speaking of blue and red, the source is militant about the color coding of the actual wires. It seems like a small thing.
It's a cardinal rule. It's what stops people from cross-wiring, which can be instantly fatal. The source cites IS codes, which are very specific.
Okay, lay it on me.
The three hot wires, the phases, are red, yellow, and blue.
Red, yellow, blue. Got it.
The neutral wire is black, and the safety line, the earth wire, is always green.
Why is that so non-negotiable?
Because imagine you're wiring a motor. If you accidentally swap a live wire, say the red one, with the green earth wire, you have just made the entire metal body of that machine live. The next person who touches it is dead, period. The color code is a universal language of safety.
We've covered the system, the map, the environment. Let's get to the human element, the armor. What stands out to you in the PPE section?
The incredible specificity. It's not just wear gloves. It is insulated gloves rated for the voltage. A pair of leatherwork gloves will do absolutely nothing.
So these are special gloves.
They're rubber, they're lab tested, and they often have an expiration date stamped on them.
An expiration date on a glove?
Yes, because rubber breaks down, it gets microscopic cracks, and electricity will find that one tiny crack. So you have to inspect them every single time you use them. Same for the insulated safety shoes.
There's a detail about the safety helmet that I found fascinating. The source insists on a chin strap. Why? That seems so trivial.
It sounds trivial until you think about what happens in an accident. If you're looking down into a panel and there's an arc flash, an electrical explosion, what's your first reflex?
To jerk my head back. Flinch.
You jerk your head back violently. Without a chin strap, your helmet goes flying off, then the blast knocks you backward and your unprotected head hits a concrete floor. The chin strap keeps the armor on when the fight starts.
That is a very vivid, very sobering image.
Right.
Okay, so you're suited up, you've got all the gear, you see a problem. Can you just go fix it?
Absolutely not. And this, for me, is the single most important part of the entire training. You need a permit to work.
That sounds like a bunch of bureaucracy. I need to fill out a form to turn a screw.
It is bureaucracy.
Yeah.
But it's weaponized bureaucracy. It's designed specifically to stop you from acting on impulse. It forces you to slow down, to think, and most importantly, to perform the ritual of prove dead.
Prove dead? That sounds like something out of a horror movie.
It's the golden rule. You turn off the breaker, you put your lock on it, that's lockout, tagout, but you never assume that it worked. You take out your meter and you physically test the wire. You must see 0 volts. You have to prove it's dead before your hands go anywhere near it.
Because if a breaker was mislabeled,
or if the contacts fuse together inside the box, if you assume it's off, you die. The prove dead step is the last line of defense.
So let's say, despite all of this, something goes wrong. An electrical fire. What does the training say?
It says your first instinct is your worst enemy. You see a fire, you think water.
And water on an electrical fire is?
Catastrophic. The water can dust the electricity right back to you. It's why the training specifies Class C firefighting methods. You must use CO2 carbon dioxide, or dry powder extinguishers.
Why CO2?
Because it's a gas, so it's non-conductive. It smothers the fire by getting rid of the oxygen.
Yeah.
And, importantly, it leaves no residue. If you spray foam all over $1 million switchboard, you've destroyed it. CO2 puts out the fire, and the equipment is saved.
This has been an incredible journey. We went from the brain, the EMS, down to the reflexes of the relays. We looked at the map. We've really covered the whole system.
It really shows that safety isn't just one thing. It's not a gadget you buy.
Yeah.
It's a complete system of systems. It's technical, it's procedural, and it's behavioral.
And even though this is all for a massive construction project, the principles really apply to everyone, don't they?
They absolutely do. Don't overload circuits in your home, check your cords for damage, and respect the fact that when a breaker trips, it's not an annoyance.
It's a message.
It's a message. The system is trying to tell you something is wrong. Don't just ignore it and flip it back on.
I want to leave our listeners with one final thought, and it goes back to that permit to work idea. Before a worker can do something critical, they are forced to stop. They have to get a permit. They have to prove dead.
That pause saves lives. It breaks the chain of error.
Exactly. In our own lives, we are always rushing. We rush to send an angry email. We rush into a big decision. What if we applied a kind of mental hot work permit to our own lives?
That's a fascinating idea.
Before you make a high-stakes decision, before you react emotionally, what if you had to stop, take a breath, assess the hazards, and prove safe before you act? A mandatory pause.
A safety stop for the mind. It lets the rational part of your brain catch up with the emotional reflexes.
It might just prevent a few short circuits in our own lives. Thanks for joining us on this deep dive. Stay safe and stay grounded.
And always check your connections. Goodbye, everyone.